One of the most important tasks that you can master as business analytics practitioners is comparing averages between two different groups. Now, we tend to do this on the daily as business analytics practitioners, and in the last homework, you got a glimpse at where this sort of application might arise. On question number 3 of the last homework, you were looking at the return rates of products to a store that sells items on TV and on a website. And you focused in on trying to estimate what the average return rate was in the data, but there's actually some additional information that was provided that we didn't actually look at for the assignment. Namely, what type of product are we looking at? Kind of opening up the data, what we have is weekly return rates for various products that are given anonymous code names. So carmine, pear, sapphire, puce, slate gray, etc. Very often, we're interested in comparing groups to one another, and in this application, we'd be very interested to see, well, is there a difference in return rates between, say, the carmine products and the pear products? If one group has a higher return rate than the other, that would indicate that, hey, we should look at that problematic product to determine why its return rate is so much higher. Is it due to packaging issues, shipping issues? What can we learn once we discover a statistically significant difference between two different groups? And in fact, on your next homework, you're going to be looking to see how music has changed over the decades. You're given information on the characteristics of some of the most popular songs over the decades in terms of the beats per minute, how energetic the song is, how danceable that song is, the positive mood for the song, etc. And we'd like to know, well, if we compare, say, the 2010s to the 2000s, do we see any statistically significant differences in the mood of the song? Or let's say the loudness of the song, or the danceability. And so this is something that we just do all the time in analytics. If we're in, say, customer analytics, we want to know what is the difference in, say, the lifetime values between customers that are men and customers that are women. Is there a certain type of customer that's worth more in the long run to the company? Or if you're working in advertising or marketing, you'd like to know if your advertising campaigns have any effect whatsoever. Is there some sort of increase in same-store sales after the week of a major nationwide promotion, say with the Super Bowl? Or did it look like that advertising had no sort of an effect? You're comparing the average sales, kind of a before and after that advertisement took place, two different groups. Likewise, if you're working in Hollywood and you're doing some sort of movie analytics, you might like to quantify the effect of having a movie being rated PG versus being rated PG-13. Is there a difference in the average return on investment between these two different groups of movies? So comparing two different groups, we've talked about before when discussing comparing probabilities between two different groups. Is there a difference in the probability of a stock out based on two different inventory control policies? And the discussion extends fairly naturally to comparing two groups' averages. So how do we do this most effectively? What do we have to think about and worry about in order for this analysis to be reliable? Well, let's go over the process. So what are the key assumptions that's going to allow us to actually do this comparison, adequately? So what do we have to assume about the data going into the analysis? Well, number one, we're going to assume that both of these two different groups, both of the samples, are a random sample from some PMF or PDF. So sample A is a random sample from PDF A. We don't know what it is. We don't really care what it is. Sample B is also a random sample from potentially the same PMF or PDF, or it might be a different one. We don't actually even have to assume that they're coming from a common probability distribution. We just have to assume that both of them are random samples from whatever distribution is making them. So assumption number one is that they're both random samples from their probability distributions. And assumption number two, this ties into when we were making a confidence interval just for an average, is that we're dealing with enough data. So to come up with a confidence interval, to come up with an idea for how much our measured difference in sample averages is likely to be from the truth, we need to invoke that central limit theorem. And that central limit theorem is only going to apply assuming that we have a large enough sample. So what does that mean? Well, it's actually tied into the shape of the histogram of the data values that we've collected. So we actually have to make two histograms, one for sample A, one for sample B. We have to look at both. If we find that the histograms of the data are roughly symmetric, then as long as we have about a dozen or more points, that's going to be large enough for the central limit theorem to be invoked and for this analysis to be reliable. In business analytics, typically we deal with some sort of skewness. So if we have some slight skewness in the distributions, then about 2 dozen or more data points is large enough to invoke the central limit theorem. And if we're dealing with a very skewed distribution, like an exponential distribution, as long as we have at least 100 data points, we really don't even care where the data is coming from at that point. The distribution can be very skewed. At least 100 data points is typically big enough to allow us to invoke that central limit theorem. So that's what we're going to assume from the data. We have basically two different samples, each of which are arising in a random fashion from their respective probability distributions. They don't have to be the same distribution. And we've collected enough data where it's okay to invoke the central limit theorem. So what do we really want to study here? Well, we're studying just the averages, basically the average of the probability distribution, making our data in sample A, the average of the probability distribution making our data from sample B, and we're looking at the difference in those two averages. So what can we measure from the data that's going to best guess what the difference in true averages is? And actually the answer is pretty obvious here. Just look at the difference in the sample averages. That's a pretty good guess. But we want to take that a step further. We know better. We know that what we measure in the sample is not going to match up exactly to what the truth is. Collecting data is a random process. We expect there to be a little bit of a mismatch between what we measure and the truth that's kind of running the real story. So how far off is the measured difference in sample averages likely to be from the true difference? Can we come up with an idea for the standard error of this difference? And the answer is yes. There's a pretty simple formula that we can work out by hand or just use software to get it out for us. And then finally, once we have a handle on that, what's our best guess? How far off do we think our guess might be? Can we come up with a 95% confidence interval for the difference in true averages here? So in order to do this analysis, we got to make that assumption that we're dealing with random samples from our probability generating distributions. And we have enough data for the central limit theorem to be invoked. The next question that we really have to answer is, are the two samples related to one another? It turns out that the answer to this question is of paramount importance because that guides exactly how we complete the rest of the analysis. So we need to ask ourselves, okay, we have two different samples, samples A and B here. Are these samples related or not? We're going to take two different paths for the analysis based on the answer to this question. And so let's kind of think through a few examples just so we get used to answering this question. So what if we were studying the same store sales, say before and after a promotion? Maybe sample A are the before sales for 50 different stores, and sample B are the after promotion sales for the same 50 stores. Well, in this case, those samples are related because we have the sales before and after for the exact same set of stores. We could go through the data and essentially match up each row on a store-to-store basis. So store one's before sales versus store one's after sales, etc. So we would say that those are related samples or paired samples. What if we are interested in comparing genders, specifically in terms of their average GPA? Is there a difference in average GPA among men versus women at the University of Tennessee? So are those two samples related? Well, I'm going to say that they're not. They're independent because for the most part, there aren't too many familial relations that are currently attending UT. So most likely the individuals in the male sample really are completely unrelated. They're independent of the individuals that populate the female sample. There's no obvious connection that we could match up an individual in the male sample with an individual in the female sample, so we would call those two samples independent. All right, well, what if we were trying to quantify the average weight loss that someone has once they participate in a diet? Maybe we have two samples indicating their before weights and another sample for their after weights. So maybe 100 people participated in this diet. Sample A are those 100 individuals before weights. Sample B is the 100 individuals after weights. Well, the data values in these two samples are going to be related. We're kind of in the paired scenario here because I could match up the values in one sample to another on a person-by-person basis. Maybe the individual in the 10th row is Fred. I can look at Fred's before weight. I can look at Fred's after weight. I can match up values across those two samples. And so our first question that we need to answer when proceeding with the analysis is, am I dealing with two independent samples? Do the data values have really anything to do with each other or not? If they don't, then we say they're independent samples. Or are they paired samples? Are they related? Can I logically match up the values in one sample to the values in the other? So that's typically the way that I figure out which scenario am I in. Is there any sort of logical way to match up those values in one sample to another? We'll go through a few different examples as we work through some of these slides. All right, so let's start out by talking about two independent samples. And so what we want to do is we want to basically figure out, well, what is the difference in average values of whatever probability generating distributions are making those data values across those two samples? And so how can we do this? Well, let's actually illustrate this with a real world example. Let's do a little bit of kind of marketing, advertising data here. Let's deal with a value that's in Reg class. And so let me load up the library cust loyalty data set. So let me load up Reg class, and let's get that cust loyalty data set loaded in here. So what are we dealing with? Well, what we have is data on 500 different customers to a particular store. And one thing we can focus in on is maybe the lifetime value of each of those customers, the total amount of money that the customer has spent, minus any sort of reacquisition costs, kind of retention costs, etc. And maybe we want to compare average lifetime value between genders, male and female, or between marital statuses, between people that are married versus people that are single, etc. So how can we do this efficiently in the data? Well, let's actually focus in on wallet share instead of customer lifetime value. Wallet share is a number between 0 and 100 that indicates the fraction of purchases of similar products that the customer makes at this particular store. So sometimes people shop at multiple different grocery stores like Kroger, Food City, Whole Foods, etc. If your wallet share is 80%, and this is a Kroger data set, that would mean that 80% of your grocery store purchases happen at Kroger. The remaining 20% must happen elsewhere here. So we can very quickly summarize the averages for different groups by running the aggregate command. So what aggregate is going to do, it's going to take a formula and a data set and a function and report back whatever you tell it to. So the way we're going to set this up is I'm going to actually put in the data argument. We're going to be dealing with the cust loyalty data set. And what I want to do is I want to calculate averages. So I'm going to say capital fun equals mean. So exactly what I want to do? Well, I want to go and look at the average wallet share for each gender or for each marital status here. So the way that I set this up is very similar to making a plot or fitting a linear logistic regression. I'm going to have a twiddle, and on the right-hand side of the twiddle, I'm going to put my grouping variable. So what column contains the group identities that I want to be comparing? So let's start out by comparing genders here, and specifically, what am I comparing about the genders? I want to be comparing wallet share. So on the left-hand side of the twiddle, that is our variable that we're using in the computation, basically getting the average. And on the right-hand side of the twiddle is our grouping variable. So if I run aggregate, what I find is that the average wallet share for men is right at about 55. For women, it looks a little bit lower, 51. I'd like to know, okay, well, is this a statistically significant difference, or is this sort of difference readily explainable just by random chance? We don't expect the averages to match up exactly when we go collect data. We expect a bit of a difference. Is this a big enough difference to convince us that, hey, it does look like we're dealing with a statistically significant difference between genders? And well, we could not only compare wallet shares between genders, but we could compare that, say, between marital statuses. It looks like married has a slightly higher average than single. We want to answer the question, okay, well, is this difference statistically significant? Kind of our best guess is what the difference in averages is, but how far off is that guess likely to be from the truth? What's a 95% confidence interval? Is 0 a plausible value, or am I dealing with statistically significant differences? And actually, something that marketing, advertising, or customer analytics would be interested in looking at is there any difference in the wallet share based on loyalty card status? So, the whole goal of assigning customers loyalty cards is to try to get them into the store more often, convince them to make more and more purchases at that store versus others. And so, if we look at the difference in averages between loyalty card owners and ones that do not, well, we have that, yeah, the average wallet share for those loyalty card people looks to be quite a bit higher, a difference of around 7.5 or so. But is that difference statistically significant? So, how do we go about doing this analysis? So, what's our best guess for the true difference in averages? How far off do we think that guess might be? How far off do we think the measured difference in averages might be from the truth? And what's a 95% confidence interval? So, how do we go about doing this? Well, the best guess, to no one's surprise really, is just to look at the difference in the sample averages. If I want to know the best guess for the difference in wallet shares between people that do and don't have that loyalty card, I'll just measure that difference in averages that I measured from the sample itself. So the sample lets me know that there's a difference of about 7.5 in average wallet shares between the yes and no group here. And I know better, I'm in analytics, so I know that this measured difference isn't going to equal the difference in reality, the difference in mu's between whatever probability distribution is making this data here. So how far off am I likely to be? Well, that's really just a question of asking what's the standard error of the measured difference. And it turns out in this case that there's a fairly easy formula to work with to get the standard error of the difference in averages, how far off the measured difference might be from the true difference. And what we do is we go and actually look at the standard errors of each of the averages for each of the samples, and we add them together in a very special way. Specifically, we square the standard errors of each, add them together, and then take the resulting square root. It kind of looks like the Pythagorean theorem. If we want to measure the length of the hypotenuse of a triangle, we square both of the sides, add it together, and then take the square root of the result. And it kind of works like that. Sometimes sample A's measured average might be a little bit above the truth. Maybe sample B average might be a little bit below the truth. And so, the measured difference that we find is, kind of bigger than what that true difference is. Other times, we might measure, say, the average for sample A being a little bit above its truth, and maybe sample B is a little bit above its truth as well. In that case, the difference in sample averages is actually going to be relatively close to the truth. And so we don't quite add the standard errors together. We want to add them in this special way. So what we could do is look to find what the standard errors are, basically squaring the standard deviations, dividing by the sample sizes. And we could use the aggregate command to help us out here. Instead of asking for the mean of each of the different groups, we could get the standard deviations of each of those groups. And we could actually get the number of individuals in each group as well by asking the length, the number of elements in each of those vectors there. So our sample sizes look like this. So we've measured a difference in these two averages of right at about 7.5 here. That's not the true difference, but it's going to be close. How far off from the truth is it? Well, if we were to type out what the equation told us for the standard error, we'd square the standard deviation of sample A divided by the sample, or by the sample size of sample A. Add that to the square of the standard deviation for sample B divided by the sample size for sample B. That's the standard error for sample A, the standard error for sample B. Add the squared standard errors together, take the square root of the result, and well, let's fix that typo here. So here I've taken that 153 and raised it to the 153 power. That's not right, but here I fixed it. So our measured difference of 7.5 is probably off from the true difference by maybe around 2.8 or so. Now, obviously, you're not going to want to run 3 different commands and then do all of this algebra to get that standard error. Let me show you a way to actually use the t-test command, which we used back when we got a confidence interval for just the average. to get the standard error automatically. So once you've run aggregate once, you've developed this formula right here, we can actually just reuse this to answer all of our questions. So if we say t-test wallet share Twiddle loyalty card, that says, okay, let's compare the average value of wallet share for the two levels of loyalty card. Notice here are our two averages right here. Those match up exactly. If I want that standard error, all I got to do is add in $STDERROR. Or I'll be a little bit more careful. I think it is just ERR. There we go. So same value here, matches up. Much easier than actually doing that by hand. So we're comparing the average wallet shares between the loyalty card owners and the ones that don't have loyalty cards. We've measured a difference of 7.5. That's close to the true difference. Just how close? Well, that estimate is probably off by around 2.8 or so. So what's going to be my conclusion? Is this a statistically significant difference? Well, I'd like to develop a 95% confidence interval to answer that question. So can I come up with a range of values that seem plausible for the true difference in averages based on the data that I've collected? And the answer is going to be yes. I'm going to skip a bunch of these slides here. I go into some nitty-gritty detail about what we have to do this analysis by hand here. And I guess I should have actually done one more thing before just jumping into it. One thing I need to check is, do I have a large enough sample for that central limit theorem to apply for this procedure to actually come up with a reliable result? And actually, when I got the sample sizes for each, the answer was overwhelmingly yes. I have at least 100 data points, and we know from that large enough condition, back from a few slides, that if we have at least 100 data points, we're good to go. We can invoke that central limit theorem to help us out. It's only if we had smaller sample sizes would I have to go and actually look at those histograms in a little bit more detail. So if I do go look at those histograms, I do have those histograms here for the slides. I definitely don't see anything that's too troublesome here. Look, maybe a little bit bimodal for the loyalty card owners, maybe bimodal here for the non-loyalty card owners. So a little bit skewed, I would say. Not extremely skewed like an exponential, which just kind of decays off exponentially. But I'm in that sweet land of having so much data that I can invoke that central limit theorem and everything is good. Okay, so what we need to know is, okay, I've come up with my best guess of 7.5. It's probably off by about 2.8 or so. So how many standard errors do I really need to go from my best guess to come up with that confidence interval? I'm going to do the same thing as what I did with the confidence interval for P, for theta, based on the MLE, and for mu, based on the sample average. All confidence intervals kind of look the same. It's your best guess plus or minus some number of standard errors. So how many standard errors do I have to go? Well, it turns out people have sat down and studied this, and they've looked to see what is the sampling distribution of t here, the number of standard errors that the measured difference is away from the true difference. And it turns out it's a t distribution, but with a parameter that's very difficult to actually compute by hand. So we're not going to compute that by hand. We're going to use t-test to actually help us out. You can do it by hand. I have some examples that go on here. You can do different levels of confidence by hand, etc. We're just going to skip to the end and say, okay, just, R, help us out. How do we do this in reality? And in fact, I've already typed out that command. As long as I've done t.test, wallet share Twiddle loyalty card right here, I actually get my 95% confidence interval immediately. So this is letting us know that the average wallet share for non-loyalty card owners is that 47.8. The average for the loyalty card owners is 55.3, for a measure difference of right at around 7.5. The standard error, our best guess for how far off that measure difference is from the truth, is right at about 2.8. So based on that, I'm about 95% confident that the true difference in average wallet shares is between minus 13 and minus 1.88. So what can I say about the existence of a difference between these two groups? Is this difference statistically significant? Well, I go and check to see if 0 is inside this range. Remember, this range of values is telling me the range of plausible values for the true difference based on the data that I've collected. And I don't see 0 inside of this range. Every single number inside this range is negative. And so I would say that 0 is not a plausible value for the true difference. And so I'm going to say that the difference in averages is statistically significant. So typically that's the question that we'd like to answer when we compare two different groups. Do these two groups have a statistically significant difference in averages? So make your 95% confidence interval and check to see if 0 is inside it. If 0 is inside the interval, then 0 is a plausible value for the true difference. We haven't detected a statistically significant difference. The data cannot discern a difference in averages between those two groups. If, however, 0 is not inside that interval, then 0 is not a plausible value. Potentially it could be that, our confidence interval always has that chance of being wrong, but based on the data that we've collected, 0 is not really a plausible value, so in that case we say there is a statistically significant difference. So our conclusion about the wallet share is that there is a statistically significant difference in the average wallet share between people that do have loyalty cards and people that don't. And our best guess for what that difference is about 7.5 here. So we can repeat that for, let's say, the difference in average wallet shares based on gender. If we do t.test, looking at the average of wallet share versus gender, we see that the 95% confidence interval, in this case, does include 0. So we would say that there is no statistically significant difference in the average wallet share based on gender. Our data just cannot discern a difference in the averages. What about based on marital status? Well, can our data discern the difference in averages based on marital statuses? No, because 0 is once again inside that interval. So one last bit before moving on, I do want to make sure that we're all very clear on the difference between what I mean by plausible and what I mean by impossible, because I've been saying that that confidence interval provides a range of plausible values for the true parameter based on the data that we've collected. I want to make sure that I'm not leading you astray and essentially saying that anything outside that interval is literally impossible or implausible. So based on the data that we've collected, we can never really outright eliminate any possible value for that parameter we're trying to estimate. There's always a chance that we just have some crazy oddball sample here. So when we are, estimating mu, when we're estimating the difference in averages between two different groups, we can't actually outright eliminate the possibility that 0 is the true difference. We're just using data to come up with our best idea of what that difference is. And to really hit this point home, not plausible, if 0 is actually outside that interval, it's still a possible value, so we can't conclusively, 100%, say that there is a statistically significant difference or not a statistically significant difference based on whether 0 is in there or not. And so let me show you this one example. If you run this line of code right here, what this is going to do is it's going to generate two different samples, a sample A and a sample B. And I failed at copy pasting, so I'll just type that out manually. We're going to set that random number seed to 116667. And sample A is going to be a random sample from a normal distribution, 35 different data points, a mean of 0, standard deviation of 2. Sample B, we're going to run runif, basically get 15 random numbers between 9 and 11 here. So any value inside that range equally likely. And so you see that by design, actually both sample A and sample B had the same fundamental average. The average of the probability distributions are equal to 10 in both cases. So once we've run that, we can say, okay, t-test, is there a statistically significant difference in the averages of whatever probability generating distributions is making my data based on the data that I've collected? Here's another way of specifying t-test actually. If you have your samples living in two different vectors, you can just have them as those two arguments. Well, we find a 95% confidence interval is from minus 2.3 up to minus 1.16. Notice all these values are negative. 0 is not inside this interval. And so the way that I've been interpreting this is I would say, well, based on the data that we've collected, 0 is not a plausible value for the true difference in averages of whatever probability distribution is making that data. But notice that 0 actually is the truth in this case by design, because the averages of both probability distributions is equal to 10. So when I say that 0 is not a plausible value for the true difference based on the confidence interval, I haven't outright excluded it. Not plausible still really does mean possible here. Okay, so for two independent samples, that's what we're going to do. We have some formulas that tell us how far off the measured difference in sample averages is likely to be from the true difference in averages. It turns out that the sampling distribution of the number of standard errors that the measured difference is away from the truth is predictable. We know it's a t-distribution with some shape. We can get that shape using some math. We'll just use t-test to do this. And so we'll focus in on concentrating in on interpreting that 95% confidence interval here. So for two independent samples, that's our procedure. What if our two samples are related? So for example, why don't I run this line of code right here? I'm going to read in a data value that I'm hosting on my website about a taste test. So in this data, what we have are individuals rating two different flavors of a product. Maybe it is a new formulation of a soda, maybe two different new flavors of Lay's potato chips, but we have data on 100 different individuals and the score that they give for flavor A and the score that they give for flavor B. So in this case, they aren't independent samples because we could match up the values in one row or one sample to the values in the other sample on a person by person basis here. So this is row 4 is person number 4. They assigned a 10 to flavor A and they assigned a 9 to flavor B. They're related because they're coming from the same person here. So in this case, the sample values are related from one sample to another. I can match them up on a person by person basis, and so I'm in the paired scenario. So how do I determine if there's a statistically significant difference in the average, say, score given to these two different flavors when my two sample values are related to one another? Well, here's the procedure. What we're going to do actually is make the problem a bit simpler, and instead of analyzing both samples separately, since they're related, we're going to create a single sample of the pairwise differences. And we're going to proceed just like what we did last week and make a confidence interval on the value of mu for the pairwise differences. So we're going to assume the pairwise differences are arising from some probability generating distribution. What's the mu of that probability distribution for those pairwise differences? So if we were going to do this by hand, we could say, okay, let's just create a vector called D, and that's going to be the values in the flavor A column minus the values in the flavor B column. D is our pairwise differences. We could look at a histogram of these. Looks to be relatively symmetric. So, in order to make a 95% confidence interval, we got to meet that large enough sample size condition. We have 100 individuals in our data, so we're already good to go. It doesn't really matter what that shape is. But the fact that we see that we have a relatively symmetric distribution lets us know that, hey, we could have actually probably gotten along with only maybe a dozen or so individuals' data here. So once we have that data set of pairwise differences here, we can just ask t-test. So what we find is that on average, the difference is minus 0.42. So it looks like that the average value for sample A is a little bit less than the average value for sample B. So flavor B is getting, on average, a higher rating from the people than flavor A here. But we don't expect the 0.42 to match up exactly with what the true difference in averages is. We expect it to be off by a certain amount, a standard error. And so once we leverage the value of the standard error with our best guess, using the central limit theorem to let us know how far off we think the best guess might be in probabilistic terms, we find that we have a 95% confidence interval for the true difference being between minus 0.8 and minus 0.027. So once again, all of these values are negative here, so it looks like that there is a statistically significant difference in averages between these two different samples. We've paired them up on a person-by-person basis. We're analyzing the pairwise differences, and it looks like that the average value of those pairwise differences is negative based on that 95% confidence interval. So we can say that we're 95% confident that people prefer flavor B over to flavor A. It looks like the average rating given to flavor B is higher than the average rating to flavor A. Now, of course, we don't actually have to do any of these manual steps like actually create that sample of pairwise differences. All we have to do is give those two different samples directly to t-test and just add in the argument paired equal true. If we do that, that automatically realizes that we're in that paired sample world. And there's our best guess for the true difference in averages, the average of the pairwise differences, and there's our 95% confidence interval. If we want the standard error of that difference, basically our best guess for how far off that measure difference is from the truth, adding that $sign STD error tells us that the standard error is right at about 0.2. So we guess about a difference of 0.42, give or take 0.2 or so. We're 95% confident that the difference in true averages is negative. It ranges somewhere between minus 0.8 and minus 0.03. So we're 95% confident, essentially, that people prefer flavor B here. 0 is not a plausible value for the true difference because 0 is not inside that interval. And so it looks like flavor B has an edge. So just as a side note, making sure that you've answered that one main question, like, hey, are we in the paired sample case or are we in the independent sample case, is actually really quite important. So we realize that, hey, these two samples are related. We could match up the values on a person-to-person basis here. If we had done this incorrectly, if we had assumed these were two independent samples, notice actually what happens. Notice now the 95% confidence interval does include 0 here. And so if we had done this the wrong way, if we had failed to identify the types of samples that we're dealing with here, that they're related, we actually would have said that 0 is a plausible value for the difference in true averages between these two flavors. And we would have come to a very different conclusion. We would have said, no preference between flavor A and flavor B. And in this case, the data actually convinces us that it looks like flavor B is a little bit better. So in the slides, we have a different example here talking about, okay, how far off do we think that measured difference in averages, once we look at those pairwise differences, is that likely to be? We have all the math that's there, but really t-test is going to be there to help us save the day. And another example, if you get you might get the completely different answer or the wrong answer if you perform that wrong approach.